This is a story about a scientific and engineering adventure unique in the history of the ocean. The water here is over 2 miles deep, and the edge of the continent is 100 miles away. But that ship is drilling into the bottom, obtaining samples of muds and rocks for scientific analysis. This is the first deep ocean drilling. What lies beneath the sea surface? There is a zone of light, life, eternal blackness, and then under miles of salt water, the red muds of the bottom with their strange animal life. Beneath the ocean floor is buried the secret history of the Earth. How can it be unlocked? This story begins in late summer 1959 with an engineering planning conference at the National Academy of Sciences. Willard Bascom, director of the Mohole project for the Academy, is speaking.
From deep beneath the ocean floor. This diagram here shows the oceanic structure, the land masses, the continental shelves, and the deep ocean basin. So far, oil drillers have worked in water as much as 400 feet deep. We must go in water nearly 30 times deeper. Oceanographers working in the deep sea have taken cores in the deep sea floor maybe 30 feet long. Our cores must reach in 20 times that far. Obviously, these are very difficult engineering problems. Now, we'll organize as follows.
Dr. Jack McClelland, chief engineer of the experimental deep drilling project. Edward Horton, drilling engineer, designer of special tools and equipment. Francois Lafayette, mining engineer, analysis of pipe stress. Peter Johnson, naval architect, marker buoy construction and installation. Robert Snyder, oceanographic engineer, current measurements.
Because of the great depth of water, it will not be possible to hold a ship in position with anchors. But if we put an outboard motor in each corner of the ship, like so, and control these from the central console, a pilot will then be able to constantly maneuver the ship to hold it in position in the middle of a circle of buoys, in spite of the winds and currents that will be tending to move it to one side. Now, let's charter the best shallow water drilling ship we can find and convert it for work in deep ocean geological drilling.
The ship selected is CUSS I, owned by the Global Marine Exploration Company. It requires a lot of modification. There are cutters and welders all over the ship. The old pilot house must be rebuilt and enlarged. Windows are cut. This space will become the control center, which will house the steering console and the navigational instruments. That's the console which will control the 4 propellers. Don't drop it. Our hopes that soar with that box would fall with it. It would take months to replace. New radar is added. Here comes a package laboratory. It too is swung aboard. Then the hook, which has been checked for flaws. The ship is canted to make it easier to install the outboard motors. These propellers are powered by 200 horsepower diesels. The shafts are 16 feet long. The propeller blades are 4 feet across. Finally, the work is finished, and CUSS I moves out of its berth into the main stream of harbor traffic. Powered only by its maneuvering propellers, it proceeds down San Diego Bay. It is registered in the state of California as an outboard motorboat. Just inside the harbor entrance, the Navy tug Coca waits. Lines are passed. The tow is made secure. The captain gives the order. The tow wire comes taut, and the long journey to the drilling site begins. When the ship clears Point Loma, it feels the great Pacific swell. Its destination is Deepwater, 40 miles off Guadalupe Island, Mexico. During the long, slow tow, engineers speculate on the task they've undertaken.
In order to be successful, this ship must hold position above a drill hole for a month. It must make scientific measurements and bring up samples of the rocks beneath water 2 miles deep. Experts of the offshore oil industry believe these experiments will fail. But we are committed. We must succeed.
Finally, the ship arrives at the drilling site. The tug shortens the tow line. Suddenly, we are free. The tug pulls away, and CUSS is on its own. Only these small buoys mark the drilling site. On the bridge, the constant maneuvering begins. These are international waters, but as a courtesy to our nearest neighbor, the mate raises the Mexican flag on the foremast. On deck, the task of assembling 12,000 feet of pipe into a drilling string begins. The first drill collar is raised to the drilling platform. It is latched into an elevator and hoisted into the derrick. Men stay it with ropes against the roll of the ship. A diamond bit is attached. The driller lowers away, and the bit descends into the sea through a center well in the lower deck. The equipment needed for this work is huge. That block weighs over 6 tons. Slips are set to hold one collar while the next is picked up. Collars are extra heavy pieces of drill pipe that weight the bottom of the drill string to keep it straight and to hold the diamond bit against the bottom of the hole. The pipe threads must be carefully cleaned to make sure that the connections are perfect and that all of the stress is transmitted from one joint of pipe to the next. The new collar is screwed in by a team of happy roughnecks and tightened with tongs to precisely the right torque. The tongs are swung clear. The roughnecks pull the slips. The block descends, and the slips are set again. A bumper sub is added. Its ability to open and close allows the diamond bit to rest firmly against the bottom of the hole in spite of the heaving of the ship. The drill pipe is painted for easy identification. Blue is the lightest pipe, red is intermediate, silver for the strongest pipe at the top of the string. Finally, we're ready to run pipe. It soars into the derrick. Slams through the gate. Is spun in with a chain and torqued tight. And down goes the pipe, one 60-foot stand at a time. 12,000 feet to go before the bit touches bottom. At 3 minutes per stand, the trip down will take 10 hours. Drilling Superintendent Woodward is watchful. Engineer Horton, on the right, explains one of his many ideas to Director Bascom. Finally, the bit is approaching the seafloor. The remaining pipe is carefully measured and recorded. The engineers and drillers go below to recheck the length of pipe dangling below the ship, preparing for the critical moment of touchdown on the sea bottom. While they do, we can examine the controls that hold the ship in position above the hole in spite of winds and currents. The XY recorder shows the equivalent slope of the pipe at the sea bottom. A small motion of that central joystick will reorient all the outboard motors and move the ship in any direction. The pilot watches the radar and sonar scopes. He makes small adjustments in one engine. And then moves the ship directly ahead. When he does, indicators show what each propeller is doing. As the propellers respond, the direction of the wake changes. The wheel changes the heading of the ship and is used to keep the bow into the wind and sea. A gyro compass and anemometer are especially helpful at night. The radar detects an approaching aircraft, which is bringing more crew members. It's a small ship on a big ocean, but it will stay in that spot a month without moving more than a ship's length. The plane flies along the coast of Guadalupe Island. We look at the complicated geological structure and hope the undersea rocks are simpler. In the sheltered lee of the island, the crew boat waits, watched by a herd of sea elephants. They're fast in the water, but on land they run like a racehorse in a tent. The men step from the plane to boat, and soon Guadalupe is left behind. The elephants resume their games as the boat heads for CUSS I, 40 miles at sea. The sea is a bit rough, but that's part of the game. There's a good 12-foot wave. So far, so good. Now, just step aboard. Our flag is flying high, and the dramatic moment is at hand when the drill bit will first touch the seafloor. The hook picks up the swivel that permits us to pump water down a rotating pipe. The Kelly is stabbed in and tightened up. Tensely, the drillers watch the dial for a sign that part of the weight of the pipe is resting on the bottom. That's it. That small flick of the needle. Now we are drilling into the seafloor. From now on, there is a constant vigil. Day and night, we watch the dials. Lafayette studies the instruments which constantly record pressure, weight, and motion. If there is a failure, we want to know why. Snyder works on the circuits of a device for measuring ocean currents far beneath the ship, which exert side pressure on the drill pipe. Chad Ohanian, our electronics expert, repairs a radio. Now the pipe racks are virtually empty. We're ready to take a test core deep within the sea bottom. A special tube is punched into the soft sediments ahead of the diamond bit. The cable and its core tool is reeled in, raising a fountain of water. Did we get a sample? The scientist is dubious. But the core barrel is laid out on the kellywalk and open for close inspection. A good beginning. After a bit more drilling and watching, another core is brought to the surface, and another eager scientist gets ready. The core is jacked out. It turns out to be a gray-green clay-like ooze. In the red light of the laboratory, the core is examined by geologists Riedel, Ladd, and Shepard. A slide is made of the material and put under the microscope. Dr. Benson of the National Science Foundation, which put up the money, gets the first look. The entire core is made of microscopic plants and animals that lived 30 million years ago in Miocene time. Meanwhile, in a small boat nearby, two divers prepare to inspect the underwater buoys. The water is very deep, but the buoys are only 150 feet down. The divers will exchange the sonar transponders, instruments that detect and repeat sonar signals from the ship, thus marking its position. Soon the divers return and pass up one of the transponders. The radar reflectors on the surface buoys are also replaced. Our scientific consort ship, the research vessel Baird, passes close alongside as the turning drill pipe probes ever deeper into the bottom. Now Dr. McClelland and Dr. Von Hertzen discuss how they'll take the temperature of the sediments hundreds of feet beneath the seafloor. Wires are connected so that the temperature can be recorded on deck. Inside this tool is a long needle that'll be forced into the sediment ahead of the drill bit by hydraulic pressure. Down goes the tool. Now it's in the bottom. The temperature is recorded. It is 20 degrees warmer 500 feet down than it is at the sea bottom. The cable is reeled in again. And finally, we see the needle-like probe. The shipboard historian, John Steinbeck, is fascinated by the sea, the project, and the men who make it go. Now, with most of the pipe in the hole, we're ready to try for a long core. The drill has encountered the hard layer of rock predicted by geophysicists. This must be the surface of the puzzling second layer. Is the rock limestone, basalt, or hardened sediment? Never before has it been directly sampled. We drop in a core barrel and proceed cautiously, but hopefully. After hours of drilling, we run in a wire to retrieve the core. The date is April 1st, 1961. The core barrel is back at the surface, and a roughneck swings it out onto the kellywalk. The tip is removed, and an eager geologist immediately takes it for a first look at the deepest rock reached. The barrel is taken apart and slid back over the plastic liner. Triumphantly, the trophy is carried into the laboratory. When it's opened, the scientists see for the first time the rock of the second layer. It is basalt, a once molten rock. Thus, one major scientific problem is solved. The director happily reports this important find by radio. Below deck in the ship's center well, the final experiment has already begun. This is a wire-line coring turbo drill, never before used in the Western Hemisphere. Water pumped down the drill pipe at high pressure causes the diamond bit to rotate rapidly. It successfully drilled the final hole of the program. The last job is to transfer the precious cores to the scientific ship Baird. To do this, it sends a small boat alongside. The sea is a little rough, but the cores are in packages that will float, and the men will protect them with their lives. The job is done. What were the scientific accomplishments of Phase 1 of the Mohole? Cores 20 times deeper than ever before were taken of the ocean's soft sediments. Surprisingly, the material was mainly Miocene ooze. The hard rock beneath the sediment was found to be basalt. This was man's first look at the Earth's second layer. The temperature of the Earth beneath the sea was found to be much greater than expected. But sound was found to move more slowly in the sediments than was formerly believed. The oceanic engineering achievements were no less impressive. In rough seas, 10 holes were drilled in the deep seafloor. One over 1,000 feet deep, proving beyond doubt the feasibility of deep ocean drilling. Drilling from an unanchored ship at a position marked only by sonar beacons was shown to be feasible. Casing was drilled into the seafloor, and geophysical logs were run. A wireline coring turbo drill was used to core undersea basalt. So ended the first deep ocean drilling. Its success opens the way to a new kind of ocean exploration.